Hey guys, welcome back, and today we're going to be looking at good old MOSFETs. So M-O-S-F-E-T. Excuse me guys, didn't mean to cough on you. Anyway, we're going to be looking at MOSFETs today. Now, what is a MOSFET? Well, MOSFETs are a transistor. And what they stand for is, I'm going to go ahead and say it, it's a long word, but it's metal oxide semiconducting field effect transistor. Okay? And we'll see in a minute why that's made the way, or named the way it is. So, okay. So, we're looking at the good old MOSFET. Okay. So, what is the picture of a MOSFET? Well, most of the time, and there are two different types. We're only going to be looking at one type right now because we're going to be very basic with it. We're going to be looking at what's called the enhancement mode MOSFET. And that is this. Now this one, and there's two different types just like the BJT. There's an N channel. This is an N channel. And then there is also a P channel type that we'll look at. Okay, so same thing. This is the P channel. Okay, so we've got an N channel and a P channel type. Okay, of MOSFETs. Now, most of the time, due to their construction, they have what is usually referred to as the body diode. Okay, and we'll discuss this in a minute. It's due to the construction of the device. Okay, it's just an inherent property that it has that. Alright, now all you need to know about these, at least very simply, is what we're going to do is we're going to look at it again in the DC world. Like, again, this is going to be very basic. This is since this is our basics stuff, so we're going to look at it as a switch. It's basically a switch that's either on, or that's either off, or that's either, let's see, we'll do it this way. We'll put a loop on it, or it's on. One of the two. So, and if you haven't seen the BJT video, I suggest you go check that one out because those are another set of very prevalent transistors that are used out there. And BJTs, which are the bipolar junction transistors, for those of you that haven't seen that video, they're commonly referred to as just transistors, whereas these are commonly referred to as FETs. There's a bunch of different types of FETs. There's, I think there's the JFET. There's a I can't remember. There's a few different types. I'd have to look at it. The ones that are most commonly used, the ones that spring to mind for me, are the MOSFETs, which is those metal oxide semiconductors. Okay, so we're going to look at just the discrete, normal, on-off state. Okay, which is going to be called the saturation region, which is when you turn these fully on. Okay, now different from a transistor or BJT, bipolar junction, is that, oops, I had the wrong drawing thing, is that instead of having a base collector and emitter, you've got a gate, a source. In fact, I'm going to write source as a cursive S because my S's look like my 5s, and a drain. Okay, here, let's do this. Let's scoot this guy where I can mess with them. Okay, alright, so there's a drain. Okay, so gate, drain, and source is what we look at here. Now, how these guys are made very quickly is there's literally in the silicon there's a base type material. Okay, and for this one, since this one is N type, this one's let's see, N type, there are going to be two little wells of N-type material, negatively charged material, in a positively charged base material, okay? And then, here, we're going to scoot some stuff around here. Let's erase this. Scoot this guy over. Okay, we're going to do the same thing. We're going to grab this guy and put him over here so I can show you. Okay, so essentially, and then what they do is they lay down silicon dioxide, and then they place another plate here, and this is the gate. This is essentially your drain and your source, cursive S. Okay, so what this does is when you put a voltage, okay, plus, and you put a voltage from here to, oh, whoops, I drew that in the wrong spot. Excuse me. And we'll look at this here in just a second. When you put a voltage source, this is plus minus, between these 2 points, and you ground this point, this is for N-type material, okay? This is for an N channel. You ground the source here. When you put a voltage here, what happens is you're going to draw electrons, okay? Little electrons you're going to draw up into this channel. And what happens is once this charges, and we'll see that, I'll show you the data sheet. Probably I may make a part 2 to this because I'm sure this one will probably be a little long like the other one. But what it'll do is when you charge it, which takes a little time, it's usually fairly quick though, because I mean, you know, you're talking, you know, little teeny tiny stuff here. So it usually takes, you know, a few nanoseconds or microseconds depending on what type you're getting, and to draw up the electrons into this channel. And what will happen then is once you get enough electrons in between these two N-type materials, is you will actually allow current to flow through here. Okay? So current will then flow. Similarly, when you take the voltage away and you ground this point, usually through a resistor, put some resistance there, usually through a resistor, it will then repel these little electrons here, and it will break the connection. So therefore, there's our switch. So that's how it makes and breaks. Okay, is it's drawing electrons up into the channel, and that's exactly what this little area right here is called, is the channel. This is the channel right here. And so you're either drawing electrons into the channel or you're pushing them out of the channel by biasing it one way or the other, and that's what it's called when you put voltage on or off. You're biasing it one way or the other. It's called either forward biased or reverse bias. And so anyway, that's what you're doing, and that's how this thing actually turns on and off, which is actually pretty cool. And that's why it's called a solid state device, is it's done with electronic charge. It is not done with any moving parts. Kind of like the BJT is done with current. Well, this guy's done with voltage. Okay? And as I said, okay, normally on an N channel, if we're going to use it as a switch, on an N channel device, the source is usually grounded on an N channel device. This provides a 0 because these turn on by a VGS, which is gate to source voltage, which means, let me write this down, move this guy over a little more, which means I have to take gate minus source, and that will equal our VGS. Oh boy, that was terrible looking. You see that? All right, VGS, okay? That is our gate to source voltage, okay? Okay, so that means we're going to put a voltage source, plus minus, from there to there. That's going to be our VGS. Yes, boy, it's hard to write with these iPad pens. Anyway, now most of these have a threshold voltage, VTH, that you have to overcome, Most of the time, generally speaking, it's about 1.25 volts that you have to go over to put this into what's called the saturation region, which means to fully turn this on where current will flow through it. You have to put about 1.25 volts gate to source on it. You have to go a little bit greater than that to turn this guy on. And that's pretty much it. These are fairly simple and very straightforward. Now, a common misnomer is, since due to the design, remember our little design here, you had the little wells, but then you have a silicon dioxide right here and then another plate. Well, what does that make you think of? Something that has two plates and a dielectric in the middle. A capacitor, right? Makes you think of a capacitor. Well, that's exactly right. That's exactly what you have there. So, which means you actually have between here and here a small little capacitor is what you have between gate and source, because of this silicon dioxide in between the actual gate and the body type material for the channel. And so what happens is you sometimes have to bleed that off, depending on how significant it is, and most of the time you will. So most of the time you will see what's called a bleed resistor, or bleeding resistors is what they'll call them. And what you do is you'll place a resistor here, usually fairly high, like 10K or 100K or something like that, to bleed off that capacitance. That way, when you send this to 0, this capacitor can discharge through that bleeding resistor. Okay? So that way it pulls that off of there. And there's also capacitance. I know, well, that one will discharge. Excuse me. There's also capacitance here as well, between the drain. That's the one that you're bleeding the most of. This one will bleed off in this direction since it's already connected to ground. This guy, however, can't bleed to ground. So, but it can through this resistor. So, sorry, I got it upside down here. So, this one's not too big of a deal, even though it is there. There is capacitance there, so it may take a little bit to bleed it off. But this one, you definitely got to bleed to ground through something, especially if your voltage is like a relay or something where it just completely opens. There's no physical tie at all to get this to ground to bleed that off. So that's where also your timing comes in. There's an RC constant there then. So you've got some RC constant, okay, that equals your time. Okay, so therefore, if you're doing any type of high-speed switching or something, you want to make sure and look, and we'll see in the data sheet, look at this capacitance, and you're going to have to size your resistor accordingly to make sure that then your RC time constant, will be at the speed that you want it to be. Otherwise, you may actually be switching too slowly, or you may be switching too fastly. It depends. It depends on how fast you bleed that off. And so that's basically something that you want to look into. Also, in most power MOSFETs and all of them, at least especially in power MOSFETs, believe it or not, in power MOSFETs, the ones that they call power, that can handle like 20 amps or like 100 amp or something like that, usually it's made up of multiple, it's made up of multiple of these. It's like a bunch of these put in parallel. So to draw it simply, it looks kind of like a power MOSFET will look kind of like this. It'll be like a whole bunch of N channels, if I can draw them all. Boy, these iPad pens are hard. That are all put together, and all of their gates are put together, all of their sources are put together to where it basically makes one giant transistor, you know, because they're all in parallel. Okay, oops, I just erased that. This is basically our drain. Okay, well, due to paralleling all these up and the way that the silicon is constructed, it will make what's called a body diode. It'll make a little diode there that will be just inherent to how it's made. And so what that does is that will cause, you always remember that even when this is shut off in this direction, if you have this in between something in this direction, you will have a 0.7 volt drop. And now to see where that all comes from, where the 0.7, I have another video that's on diodes that you can watch. And that will help clear up some of that. So now we're going to look at, let's get this out of here. Okay, so that's basically where that diode comes from, is it's due to the construction of it. So a lot of times when you see one that's just a regular small little MOSFET, usually won't have that body diode. Sometimes they can, sometimes they can't. It's really up to the manufacturer how they make it. So you just pay attention to the data sheet and see how they make it. So anyway, that's basically it for, oops, I don't want to clear the page. That's basically it for that explanation. So that is a common gotcha, is that bleeding resistor. You definitely want to remember that. Now, the other one that I want to show you is the P-channel version, which we've always said, I even said in the BJT one, the P-channel is basically the reverse. Okay. It's basically an N channel, but upside down. You still got your gate, your drain, and your source, and here we'll show the body diode for the whatever for purposes of the power diode. Anyway, so we've got this. This is a P channel. Okay, channel. Now P channels still the same thing. They turn on. Oh, I'm sorry, I just labeled that completely wrong. It's upside down compared to the N channel. So this is actually the drain, and this is actually the source. Okay. So most of the time, if you're just using it as a switch, again, we're using this as a switch. We're doing very basic. You're going to tie this to a high instead of a low. You're going to tie it to a 5. This is basically a high side switch. Okay, I forgot to mention that when we were talking about the other one. An N channel is considered like a low side switch, or switching a ground or the negative terminal. Whereas a P channel is mostly used, when it's used as a switch, it's used as a high side switch. So which means we're going to bring in the 5 volt and it'll switch the 5 volt line, or 3.3 or 12 volt, or whatever your application is. It'll switch the high side. So now you're going to want, again, a voltage from gate to source. Okay. You're going to want a gate to source voltage. Now, in this instance, if you look at data sheets on P channels, you'll see that the trip voltage is negative. It'll say that the threshold voltage is negative, like 1 1/4, something like that. Well, it's because, again, still, even though it's a P channel, it turns on gate to source. So your VGS is still your VG minus your VS here. So now that goes to show you that if you put excuse me, if you put 5 volts on this, remember a P channel is the reverse, and when you put 5 volts on it, it turns it off. Okay, so if I put 5 volts on it, what's going to happen? I'm going to have, because this is connected the way it's connected, I'm going to have 5 minus 5, it's going to equal 0. So if I put 5 volts as the gate voltage, I'm going to get a 0. See, I'm actually going to get 0 volts gate to source, which turns this off. So it's the reverse. So a high turns it off instead of a high turning it on. An N channel, you put 5 volts on it, it turns it on. But if I change this around and I give it a 0, I take and I let's see, I'll just erase this. I take this out, and oh my, I didn't mean to erase all that. Undo. I take this off and I ground it. Ground it, if I can draw a ground symbol. If I ground it, now I've got 0 minus 5. I get negative 5 volts. Okay, guess we better put volts on everything. Keep your units. Now I have negative 5 volts. Now, negative 5 volts is over that threshold. Okay, and so it turns it fully on. Okay, so just the reverse. So 5 volts turns it off, 0 volts turns it on. So that always helps if you want something that's basically initially on, and then when you give it a high, you know, basically just doing reverse logic. These help a lot. And then, you know, it's the same thing still whenever you turn these on. So if I go back, see if I can go back far enough. Undo, 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 undo. Oh, it does go back far enough. All right. When I do this, now current can flow this way. Okay. So if current flows this, well, technically it is the other way. It flows high to low. Technically, my bad. It is going to go like this. But anyway, so there you go. So that's essentially a P channel. How a P channel works. So now I'm going to stop here, and we'll grab. You know what? Actually, I don't think this movie's gone too long. Let's go ahead and look at the data sheet, shall we? I've got it right here. This is a MOSFET. I chose this MOSFET. Excuse me. Gosh, got frogs in my throat. All right, this is a MOSFET. The reason I chose this one is very simple to get a hold of. You can find this at your local Radio Shack if you have one. Usually these are easy to find. It's the good old 510A, the IRL 510A. Anyway, it's a logic level device. Basically, it has a drain to source voltage of 100 volt, so it's very good. There's this RDS on. What that is just like anything else. This thing does have resistance to it. It has a channel resistance. Remember me talking about the channel? There's actually, if we want to look at it, when you look at the, oh my iPad's doing funny things. When you look at that, you know, when you're looking at this little piece, essentially this channel isn't perfect. There's some resistance to it, essentially. You know, and your current's doing this. It's going through from drain to source. You know, your gate's up here. This is your gate. There's some resistance there. Okay, so when we look at it in symbol form, okay, like this. Okay, there's actually, imagine, kind of a resistor there. This is the RDS, I call it on resistance, is what that is. So that means when this guy is fully turned on, so it's fully forward biased, means, you know, you've given it, let's say 5 volts or whatever that's over its threshold voltage, and it's fully turned on, it has about 440 milliohms worth of resistance to the channel, to that channel. So essentially when that switch turns on, it basically adds a 440 milliohm resistor to your circuit. Now a lot of times we're just doing microcontroller stuff and whatnot. That's so small it doesn't matter. It doesn't matter with anything, but it depends on your application. You may have something that matters, so you may want to select one with a lower RDS on. And I've seen some that are very, very small, so they are out there. It has a ID, that's a drain current of 5.6 amps. So this guy can take 5.6 amps. So he's kind of in the power side of things. He's a power MOSFET. He's in this nice TO220 package, so you can get the heat out of it. And now let's go ahead and look at some of the properties of it. So again, it reiterates that we've got our drain current and our other currents, and gives you some temperature information and whatnot. Package dissipation, wattages, all that fun stuff. And then we've got, see, there's even one that says peak diode recovery, because it's got that body diode they were talking about. And oh, gate to source voltage. This is a good thing to note. See this gate to source voltage, VGS? It's telling you that this can take plus or minus 20 volts on its gate to source. If you go any higher than 20 volts, you will damage the gate. And so that's another thing why you might want to put protection on your Zener depending on what's driving it. You might want to put a, or on Zener, you want to put a Zener on your MOSFET, on the gate of your MOSFET. Let's say if it's being driven by something that could have the potential to shoot higher than 20 volts. Let's say if you have a 48 volt power supply and you're regulating that down to 12 volts or something like that to power this with. If there's ever a chance it could short and send 48 volts to this, it'll blast it. So you might want to add protection to that, which we'll look at, and I'll do a protections basic video later on in our series, but for right now we'll just concentrate on this. There's your power dissipations, yada yada yada. Here's that RDS on again, on state resistance, and it gives you their test criteria, what they tested it at. And here's your typical min and maxes. Okay, here we go. VGS-TH is what they call it. So this is the gate threshold voltage. Okay, see that? So anywhere the minimum is 1 volt to 2 volts, this thing will turn on. So it would be my recommendation to never get in that area where it's kind of undefined. Like it's basically they're saying 1 to 2 volts. Don't do 1.5 volts. Because you don't really know, and I wouldn't really do 1 volt, and I really wouldn't do 2 volts. And remember, nothing in the world is perfect. So, even though you learn in school that, oh, it's 0 or 5 volts, it's 0 or 5 volts, well, technically, they range, and that's what they're telling you here. They range. It's anywhere from 1 volt to 2 volts. You know, some, you could get like 10 of these, and 5 may turn fully on at 1.5 volts, and 5 may have to be turned on at 2.5 volts. So a good recommendation is to stay above that, but yet under the maximum threshold of 20. So a good bet is like for what we're doing with microcontrollers, whatnot, 3 or 5 volts, you're going to be golden for this guy. You're going to be perfect. It gives you gate source leakage, forward voltage, all that fun stuff, because there is leakages to these guys. That they do. You learn in school that they do not draw any current on the gate, and that's what's so magical about these. They draw 0 current, unlike a BJT draws, you know, all kinds of current on its base to turn it on. Well, these just work off of voltage. Well, not necessarily. Just like everything else in the real world, it does draw some current. Now, it's very tiny, but depending on what your application is, if you're dealing with, you know, if you're creating some sort of a meter that reads stuff or something, that tiny current might be significant. So you want to pay attention to your leakages, and that's what these gate source forward and reverse leakages are. Like, see, it's 100 nanoamps and things like that. It's very small. But if you're working in nanoamps and you're doing nano, you know, watt technology and stuff like that, where everything's in nano and everything like that, then it may matter. It may cause problems for you. So, excuse me, I'm sorry I keep coughing. I've got, I don't know, something going on here. Allergies. Anyway, there's a drain to source leakage current, which means when it's turned off, you know, it may, when you get up, you may have anywhere from 10 to 100 microamps, you know, leak through it when it's turned off. You know, things like that. Just things to be aware of. Things to be aware of. And then if you look at this input capacitance and output capacitance, here are all your capacitances that I was talking about. You have a gate to source capacitance, you have a gate capacitance, source capacitance, drain capacitance, and then everybody in between. So essentially what it looks like, if we want to draw it very simply, let me see if I can't get this to clear the page. To draw it very simply, okay, here's our N channel. You've basically got a capacitor here, you've got a capacitor here, you've got a capacitor here, and you have capacitors here. Oh wait, no, oh, sorry. That's it. That's all of them. You've got capacitors all over the place on these things. They have lots of different stray capacitances. So you've got at least 4, and I think there's even more. I'd have to look it back up to remember where they all are. But that's essentially what they're telling you here is they're giving you all those capacitances. And then see, they even give you turn on time delay, rise times, and then they're telling you total gate charge. They tell you that in nanocoulombs. That's telling you how you use that to figure how long it takes to charge the gate, to actually draw those electrons up into the channel. And like I said, most of the time, none of you dealing with microcontrollers where you're just turning stuff on and off, you're never going to probably get into this. But if you get into stuff where stuff needs to be done quickly and done very speedily and everything else like that, then this stuff starts to play. So I just want you guys to just see it and just kind of me explain a little bit of what it is. And so these gate charges and whatnot, you may come in to have some significance because you have to bleed that gate charge off, or you have to charge it. So there's actually a turn on time, and that's that rise and fall time. And there, see how it says C figure 13 on that rise and fall time? It's because it all depends on how much current the gate can draw and what kind of bleeding resistor you've installed and things like that. So they'll give you on figure 13, there'll be some graphs. And see, here they are. They're going to give you all kinds of graphs that show you at different currents, at different voltages, gate to source voltages, drain to source voltages, all of those different parameters are going to show you in these figures how this thing responds to all that, and speed and all that. But like I said, most of the time, you guys are just going to ignore all that. You're gonna be worried mainly about what's my absolute max stuff, like what's the highest voltage I can put drain to source, what's the maximum current I can push through it, and maybe you'd be worried about what's the resistance of it, and you want to know what's the maximum voltage that I can work with. So anyway, that pretty much sums it up for the MOSFETs. That was the 510A, and they're generally all pretty much the same, how they work and whatnot. Power MOSFETs, yeah, a little bit different. There's a lot of different types. There's planar and trench and all that stuff. But for the basics, what you guys need to know is basically they work like a switch. You give them 3 or 5 volts, just like what the microcontrollers put out, gate to source, and they'll turn on and they turn off. And N channels are basically positive logic. 5 volts gate to source turns them on, 0 volts turns them off. And a P channel, 0 volts gate to source turns them on, and 5 volts gate to source turns them off. And P channels are high side switches, N channels are low side switches. And I think that's pretty much it that I wanted to show you about MOSFETs. So hopefully this was informative. Hopefully it wasn't too awfully long. I know I went quite a ways. Sorry about that, but I really want to give you guys kind of a well-rounded idea. And like I said, a lot of the misnomers, like those gate chargings and things like that, and like the bleeding resistors. Always make sure you go gate to source with some sort of a bleeding resistor, like I said, 10K, 100K, something like that. You could get crazy if you want it to be you know, if you wanted it to not have hardly any leakage, gate to source, and put like a mega ohm in there or something. But a lot of times if you do that, you may start seeing some slewing, but then again, you may not care. So, you know, just play with it, experiment with it, put a scope on it, see what it looks like turning on and off, and see what you can play with. So main thing is have fun with it all, guys. And you know what? I think we're pretty much done with time. I've rambled on way too long. So with that, I think it ought to do it. Take care, guys.